Mhm. Okay, while we wait probably a couple of minutes, let me delete what we just did in the other session because we're going to be using the same materials. Mhm. I uploaded with the slides some one Excel file that is called brass. We're going to use that this morning. So please get that. And okay, and I think I deleted everything. Yes. Give me a second. Hello, hello, hello. Okay. Sorry, these 15 minutes between classes is like get a new coffee, take out the dog, and technical scales, whatever. Technical stop for whatever I have to do, and then coming back here. Oh, this is being recorded. Okay, anyway. So most of you are here. So to announces tonight, well, tonight again. Sorry, I've been saying tonight since the previous class. Okay, this morning we are going to see the last of the mortality components of this course. So the evaluation for life tables and for mortality is already available. It is a really nice example of life tables applied to a different context than mortality. So remember that you have all these days to work on that evaluation. Is really well, I say I think it's really an easy one. And at the end of the semester, because I was going through the agenda that we have, and then I realized we had nothing for March 13. There was nothing there. I was like, what? So I came out with the I found out that I had an additional day for teaching. So I changed a few things from the agenda, but again, the good thing is that now we will have more time to explore survival models, which I think are really useful, and now they are really popular, and they are nothing but advanced life tables essentially. And last night I was already working with some R code for that thing. And tomorrow we are going to start talking about fertility. So again, you already have the information that we need, so you don't have to download anything new from INEGI, or I am assuming that you downloaded the information that I asked you last time. So that's fine. And yes, what else? Okay, so since the evaluation is available and you have to work on that and so many things, for the activity that is coming out from this session, you only have to choose one of the things that we're going to see this morning. So you don't have to do everything, and you will see again why. So just choose one of the things that we will see, and you can upload that. And let me share my screen with you. Okay, so this morning we're going to talk about models in mortality or for mortality. And remember that here we're using the word model as just one representation of reality, or one representation or one approach to measure the impact of something. In this scenario is mortality on survival of one population. So we already know models because we have been using life tables, and one life table is one model. We are essentially keeping track of what is happening to our population. You're familiar with Gompertz and Mayhem. For those of you who haven't taken the actuarial mathematics class, we are going to explore these models in that semester. But what I'm thinking is, by the end of the semester, I want to, because now we have life tables, and we are going to see how to open those life tables for individual ages, which essentially is what we need to estimate actuarial present values for insurance and for annuities, right? So you essentially could estimate any prime, sorry, any premium. I need more caffeine in my life. Any premium using the life table for your stake. However, it is sometimes really neat to have the expressions for Gompertz and Mayhem, and so you can essentially model to any specific or exact age. So I have been exploring some models in R that, well, some libraries in R that give you the parameters for Gompertz and Mayhem, but the ones that I have found are kind of weird in the sense that they use different expressions, and again, those are essentially transformations of the expressions that we have. So I decided to wait for the end of the semester, so we can explore those things. So probably just give you the R code and some examples to estimate those models. But what we're going to essentially spend most of the time this morning is talking about Brass relational model. This is a really nice model because, well, I will explain you more about William Brass, but many of you, at least one person from this session, but I know somebody else emailed me last night, I don't remember when. Some of you have found issues with your life tables. When you were trying to work your life tables to age 100, and suddenly, if your population was really small, you had lots of deaths, or you have fewer deaths in from the what the logic would indicate us. So you were finding really high life expectancies for those ages, and so what I told you was that, okay, instead of going all the way to 100, just leave it to 85 and older, and that's it. That's fine. We can work with that. But what if you want to estimate your life table for older ages? So that's what we are going to do right now or this morning. And I decided that I am going to do something. Again, I have my life table for ages 100 and older, but that's because I have Mexico, and the likelihood of me finding deaths for specific ages is really high. So, and then we're going to see how to open how to estimate survival for really old ages, which is something really neat. Okay. So if we want to model probability of death or survival for our populations, and this is not the pencil for this thing. Okay. We are going to find some issues, or here what I'm saying is we have some sectioning to do. Why? Because let's say that we have our two functions here. And this is going to be qx and lx. So for most of you, or for we found for a probability of dying, this J-shaped pattern that we have here. And for those dying, if you plot the survivors from your life tables, you find a decline at the beginning, then something like this, and then of course this is I am making these things really extreme, or with really clear shapes. So if we want to model these things, it's really complicated to find a model that is going to fit all these things. So what we usually do is we kind of split this into sections. So we can model this decline in mortality when we have really high mortality, and that's the reason people are dying really fast, and then the reduction. And then we have kind of almost a linear trend here, and then we have something happening that really old ages that again is resulting in these shapes being like this. And what we're going to do tonight, essentially, we're going to pay attention to this area down here, which is probably the most complicated to model. And now that we have aging populations, we have more people reaching those ages, it is probably something that we should be paying more attention to. So what options do we have? Okay, let me open this chat here because I don't see if you write something there. So as I was telling you, we're going to use this Brass relational model to fit the general pattern for general mortality. So lots of general here. Sorry, I usually do these things really late at night. And then we're going to use Gompertz to estimate very old ages, or survivors at very old ages. And again, we don't have time to find all the expressions, to develop all the expressions, but in general, essentially for Gompertz, that's the reason I was thinking about leaving Gompertz to the end. If we have an additional session over there, we could just spend it developing expressions for parameters for the Gompertz function. But we're going to start with this first model. First, William Brass was probably one of the most prominent demographers working in what we call mathematical demography or formal demography. And even though this sounds like how crazy are you now, we're using really basic stuff, but remember that demography is kind of well, it's a social science, but we have people coming from actuarial sciences, from statistics, mathematics, but we also have people coming from sociology, anthropology, and well, I had engineers in my cohort in the master's program. So again, we have people from different backgrounds. So what usually happens is that actuaries, and in my cohort there was a mathematician, we are comfortable using integrals and derivatives and partial derivatives and differential equations. And when we use those things, most people are like, oh, okay, this is something that we don't want to explore. So that is what we call mathematical demography, just essentially using these expressions to model things. And it's not that different from what we saw at the beginning in actuarial mathematics. But so this guy was a pioneer in this area. And what he did was he explored information regarding mortality in sub-Saharan countries and in some other countries without good demographic information, because that is a big problem that we have. Even nowadays, we have countries without information. And of course, we want to have some information about that, or not even countries. I think I told some of you, what if you want to get a life table for one municipality in Mexico? And yes, if that municipality is Ecatepec or Ciudad Neza or Iztapalapa, you have lots of people. And essentially, even the population in those municipalities is more significant than population for some states, right? So you shouldn't have any issues. But what if I want to get a life table for my municipality from the small, well, it's not a small, but the unpopulated municipality where I was born? Again, I will face some issues there because I don't have information for. Well, I have information, but I don't have people dying every year at every single age. So chances are I'm gonna find spots without, or ages with zero people dying at that age, and that is a problem when we are trying to model, because we know that zero is not really a zero. Probably nobody died that year, but the previous year lots of people died. So that's the reason I had mortality happening 1 year before, or it could happen 1 year after the year I am using to estimate my life table. So we have to find a way to estimate life tables even if we don't have information. And this is important. And I was telling the previous section, I had this friend. Well, I have this friend. She's from Bolivia. And during the master, her thesis was essentially get a life table for Bolivia. That was it. The things that you have been doing these days, she did that, but again, the problem was that she didn't have any information. She went to the Bolivian INEGI, I don't remember what's the name of that department there, and she had to copy by hand from some books some information because they didn't have any things in electronic format. So, and then she came back to Mexico and she spent 1 semester essentially creating a life table for that country, which is, again, something really important for them. And then she got a really nice job at CEPAL, and now she lives in Santiago. But again, sometimes we have to do these things. So let's estimate or let's model our life tables. And what we're going to do right now is we're going to use this model to kind of smooth or improve the quality of our life tables. This is something that you don't have to do. Okay, you have to do it for the activity, but in reality, we usually don't do these things unless we want to smooth this information. Okay, so let's work with some changes in our variables. Let's start with this new notation, and this new notation essentially comes from mathematical demography. So what we have here is the probability of surviving from age 0 to age x, which is something that you should probably know how to write in actuarial notation, right? Because what we have here, this px, is essentially probability of surviving from H0 to Hx. This is the notation that we have before. And remember that this is different from this. Okay, so this is the third one is the one that we have in our life tables, but now we want to estimate to get the other two. And it's not that complicated. We can do it. It's just taking those surviving to Hx and then dividing them by our radix or 100,000 in our life tables. And of course, if we have the probability of somebody surviving to Hx, we can have the probability or the cumulative probability of dying between H0 and Hx being 1, or the complement of this probability of surviving, right? Okay, so let's start with, now let's not do this yet. So let's talk, why do we need this? So we are going to create this model. And in this model, sorry, give me a second. Okay. Okay, sorry. So what we're going to do is, and this is what William Brass decided to do. He said, okay, you have your probabilities. Let's use this transformation to try to make these things look linear. And again, that's the reason I told you, okay, if we pay attention to this section of the probability of dying, and this was just for the regular QX, and we can plot these new probabilities of dying to see how linear they are. And he said, okay, if they are linear, we can model this following a linear approach, essentially trying to fit this a linear expression to this thing. And yes, this looks pretty similar to the things that you've been doing in econometrics, but in econometrics, what you have is essentially you are modeling continuous variable using a linear expression, right? You have beta 0 plus beta 1, x1 plus beta 2, x2, and so on. I really don't know how far you are in that class, but that's the general idea. And with this in mind, let's start thinking about this. Okay, so what values can this probability take? Just a basic question. This is a probability. So what are the values that this thing can take? Come on. I refuse to move before you type the answer in the chat. Exactly. Thank you, Ana Sofia. We know that this probability can take values between 0 and 1. Okay? If we use this transformation, let's ignore the 1/2. Let's talk about the log transformation of this. So if this probability is 0, everything here is 0, right? So the log of 0 is no, no, no. Well, it's not that it's no, no, no. We know we got that value, okay? And if this probability is 1, this goes to, goes to 0. So again, by using this transformation, we are forcing these probabilities to move, instead of being between the 0 and 1, to move between the negative infinity to the infinity, okay? No, sorry. Yes, 0, yes, no, I'm fine. So that's in theory what we are doing. So now, if we have this, we are transforming our probabilities that are, yes, it's a continuous variable, but it's a continuous variable in one small interval. What we're doing is we're moving this variable, and then we're just very about 1/2. So again, negative half infinity to one side of negative. So again, it's just infinity in both sides. So what we're doing here, we're transforming our variable to be able to cover all real numbers, right? And that is the definition that you actually need for regression to model these things using linear regression. Okay, I don't know if you discussed those things, but yes, those essentially, that's the requirement for the dependent variable is to be a continuous variable, and that means I can take any value in the real numbers. So what we're going to do is we're going to get this transformation, and this is what we call this new variable, because again, it's really complicated. It's not complicated, but it's time consuming to type logic all the time. And we're going to make this transformation to estimate a new model. And once we get the estimated parameters, we're gonna move back to get our probabilities and then create our new life table, but with new and improved information. Okay, so right now it's kind of a lot of things. But what we are going to do is we are going to use one standard. And the standard that we are going to use, here's where we can get creative. For this session, we're going to use William Brass's standard. He came out with one standard for the population for any population. Okay, so that's what the one that we are going to use. So what we are essentially going to do is we have the values here. We will fit one straight line, as straight as that looks, and then using this standard to get the new predicted value. So these points are the observed values that we have, and now we're going to get a new value for our logit, and then we can take the opposite transformation. So I don't know if the general idea is clear here. But this is again what you have been doing in econometrics, or the general idea of econometrics class that you have. So, but here what we have is we have one like line of one dotted line. For econometrics, what you usually have is one cloud of points. But again, it's just the same logic. Okay, so let's start talking about the standard. And this is information that I included with the slides. It's on Blackboard, so hopefully you have it with you. What he provided, or what he gave, was the values of the logic transformations. So these are values that actually I went online, and I don't know if I put it here. No. I can send you the link for the United Nations manuals that we have for these things. So United Nations has, in the population division, they have all this information for techniques. There you can find Whipple, you can find Myers. There's another index that we didn't discuss that is called the United Nations Index. There are things to estimate these models and so on. So United Nations has all this information available, but you have to know where to look because they have lots of information, and sometimes you have to learn the path to reach these things. So William Brass gave us these standards. So what we're going to do, we are going to use this as the standard population to improve our life tables. But again, what if I give you, I can give you the standard for Mexico, and then you could use the national standard to improve your state level life table. Or you can use your state level life table to get the municipal, the life table for the municipality that you're working with. So again, this is really, really useful. So I'm gonna start this thing, but by choosing to end my life table at age 85 and older. So again, because some of you couldn't reach your life table to age 100, that's fine. I'm gonna show you how to get your life table for any value. So let me see. Okay, this is the other. So let's start with this. I need to get the transformation for my probabilities of dying from age 0 to age X. Here I'm going to be working with the Mexican male population in 2000, essentially the life table that I have for men in 2000. But we could do this for women, for the total population, for any year. Again, what I'm asking you to do in the activity is just one. Again, it's up to you to, okay, if you want to do all of them, that's fine. So according to this, the transformation that I need to do is here. Is 1 subtracting this probability. Okay, so let's just get that. So it's 1 subtracting, let me go here, males, this divided by this same. So of course the first one is going to be 0 because the probability of you dying before age 0 is 0 because then you are not in our population. Okay, and I'm gonna get this all the way to 85. Just like that. Are you there with me? Yes? No? Okay, wonderful. Now, here, of course, I already have here the logic transformation for the standards, but again, let's estimate it, them again. Here I have for the standard population and for my population, the logic transformation. So let's get the logic transformation here. So it's 1/2 of the natural log of the probability divided by one, well, by the complement of this probability, okay? So it's gonna be 1/2 of the natural log of this probability, one this probability, okay? And of course, we get error because we are trying to get the log of 0, but don't worry, we get rid of that. And here. And this is the same thing for the next one. I can just copy and paste the formula. So these are my two logic transformations. Okay. So right now we are just transforming our variables. Nothing weird is going on, but we need to get the values of alpha and beta. Again, what we're going to do is we're going to assume that our new estimated values for the logic of our state or of our population is nothing but a linear transformation of one standard, right? And this linear transformation is affected by these two parameters, beta and alpha, and these two are estimated using our population and the standard at the same time, essentially what we're doing here. And you can see this as in your econometrics class or just as in your matrix class. It's just a linear transformation what we're doing here, okay? So yes, those things actually are used in real life. So let's find these values. How are we gonna find alpha and beta? Have you discussed those things in econometrics class or not? Hopefully, yes, it's almost half of the semester. Okay, thank you. Yes. Yes, I was about to start like texting Mike. Okay, so yes, we can use least squares. And again, I'm guessing you're using R to estimate these things, but we only have one variable. We only have few observations. It's nothing complicated. So we have two approaches. We can use what we have used before, using a scatter plot and ask Excel to include the equation, which is one easy way. Or we don't like plots. Look, I already have the values here. Let's get the values for alpha and beta. Okay, let's get these two values. So alpha is the intercept. Okay, so Excel is wonderful. It already has the function intercept. So I need to give the values of x. Remember that I decided to, well, y first. X is going to be the standard. Y is going to be my population. So first I give the values of y and then the values of x. And if you compute this in Spanish, the function is intersección eje. I think it's something like that. Intersección eje, or yes, I think. Just if you compute this in Spanish. And now beta is just the slope, or pendiente. The function in Spanish is pendiente. Again, first giving the values for y, comma, and the values for x. So there is no need for a scatter plot. We just have the values for alpha and beta here in our with Excel. Okay. Well, so I'm guessing. Well, I'm assuming everybody's there. Remember, first goes y, and there goes x, and is intercept in English or intersección eje in Spanish, and then slope or pendiente in English. Okay. So now that we have these values of alpha and beta, using the standard, I can get the estimated values for my population. So that's what I'm gonna do here. So first, I will not get this because again, it's a problem with the zero. This is going to be alpha plus beta times the standard. Just like that. And double click here. Okay. Now I can get the expected or the estimated values for my probability of dying before reaching age X. The first one is easy. The first one is 0. That's one we didn't even know. Well, we didn't even need the value for the logic of that because that's 0. And then use the transformation again. This is just clearing this expression. Sorry, this expression for Q. So that's what we're doing here. Going to be expected value of 2 times this, and plus expected value of this, or not expected value, the exponential value, times 2. And we're almost there. And now I just can estimate the probability of surviving, X, and then the survivors are going to be 100,000 times this probability. And again, but I told you, we can estimate these following values here. That's something that we can do because since we have alpha and beta right now, I could go here and use these values to estimate any value that I want for this Brass relational model. But the only problem that this has is that it stops at age 99. So that's our last age. But again, it's not a bigger of a problem. But let's not do that yet. But we can compare. Let's compare this new information. It looks like a survival function. That's fine. With the one that I had before doing this. So it was 2000, right? And all the way to age 85. And yes, and you can see what we're doing here. We're just improving this part. And again, there are some differences here. But again, this is just one option. And probably using Brass standard is not the most appropriate option, but this is just an example. If I give you one different standard, you could do it without different standard without any problem. Okay. But yeah, so essentially what we're doing is just changing the shape of our function. And actually what we do sometimes when we're working with projections, we change the values of alpha and beta because this is what we, okay, let's change these values to 1.5, sorry, 15, I did. No. You can see if here I am increasing or making more negative the value of alpha. What I'm doing is I am increasing the probability of surviving for my population. Okay, so I'm just gonna change this, and I don't think I would have one positive value. Well, this wouldn't be for a human population, but again, I could have something like this without any problem. And if I change the value, so essentially alpha is giving me the shape, like how fast my population is dying. And with beta, is giving me, again, like this, how compressed is the probability from, like, for the last ages. Again, everybody has to die. So what beta is doing is like pushing it to like people are gonna die in a faster way. But again, this is what we usually do. This is another approach to work on projections. Sometimes we don't work on projections of these things, or survivors, but if we have information for several years of alphas and betas, we could try to project the value of alpha and the value of beta, and then estimate our new life table. Again, this is just, I am just giving you time to reach this stage. So are you there with me? So did you get these values? Okay, so now what? This is a really neat average life tables, and average life tables actually means in age groups. But what if we want a complete life table? And that makes sense because remember, in actuarial mathematics last semester, I was telling you, you need the probability of this person reaching every single age and then bringing that to present value using our rate of interest, whatever. So I need the information for every single age. So can I get that? Yes. We just got these parameters for my relational model. So remember that I have this expression, and this standard that I'm using here is the standard that I got from using this for these specific ages. But I have this information for every single age all the way to 99. Well, I could get my estimates for every single age. Again, the first one we don't need. The second one is going to be this same value of alpha plus the value of beta times the standard that we have here. And are you good to go? Let me see, because sometimes it goes. Yeah, that's fine. And here we have an issue because, again, this cannot be 0. So there we are. And now that we have that, we know this is 0. This is the exponential of this times 2 divided by 1 plus the exponential of this times 2. Yes. And then get our really nice life table for individual ages, which again is something that we already had. And then I can get like all the information that I need for my life table from this new. Okay. What is going on here? Oof. And again, this is gonna, yes, it doesn't look that smooth, but again, for those of you who told me, the problem my QX looks like it has these ups and downs, and it's kind of weird, and it's not actually fitting really smoothly and everything. This is a way that no, use the tables that you have. Again, you don't have to do this unless you want to. If you want to use this thing, you just have to let me know. And again, you can tell me, okay, I decided to use Brass relational model to improve the my life table. That's fine. It's something you can do, but you don't have to do it because, again, the problem that we have here is, okay, if you want me to, I can share with all of you the information for Mexico, because remember that here we're using the standard that is a standard for any population. Again, it's not probably the best option, but if you have the standard for Mexico, you could use that for your state. But again, you don't have to do this. This is just something additional, okay? So again, but this is, again, how we can actually get our life table for individual ages. But again, we're gonna go from age 0 to age 99, and that's it. And this is useful because, again, this is the way that this is how we need our life tables to estimate premiums and estimate all those things that we discussed last semester. Okay, questions here? No. Because there's another thing that we can discuss. And it has to do with these very interesting age groups. So for all their age groups. Let's say that you don't want, and it is right here. So yeah, I am not just jumping to new conclusions. So let's say that I don't want to open my life table from an abridged life table to a complete life table. I really don't need that. I am not working in insurance. I'm just doing some estimates for the governor of this state, whatever. But I do want to get my life table all the way to age 100 or 105 or 110. Again, can I do that? Yes, we can do that. And the way that we do it is just paying attention to our last 3 age groups, and because we need at least 3 uh, points of observation to fit our Gompertz model, but only to this interval for the last part of our survival function. Okay, and that's what we're going to do for this. Again, if you don't want to do the branch relational model, that's fine, but you have to do this for your activity. But for your submission, that's fine. You don't have to do these things. So, and this is answering the question that some of you asked me, like, oh, but I want my tables to age 100, but I told you, but then I told you, okay, no, stay to 85 and older. We can change those things. So we're going to use the Gompertz law of mortality. That is, again, something that we have used before. And the good thing about finding out that I have an additional session, remember I told you that I just found out that the March 13, I didn't have anything for that day. So that we can have one session discussing how to fit or how to actually find these parameters using R or using one library. But again, that is something that we could discuss at the end of the semester. Or if you want to do everything by hand and finding these values, that would be really an interesting, good extra credit for you. Okay, let's see how I feel about this later in the semester. So what we're going to do is we're going to take our 3 last age groups, and in this scenario, the value that I decided to have as my starting point is the survivors at age 75. The length of my interval is 5, and X is 75, right? So using, again, remember that here, in order to make this thing look more like a linear expression, we use a log transformation, so we can move the B down here, and then we work with those things to estimate these expressions. So we reach these expressions that, again, look kind of complicated, but just because of the notation. So in reality, if I start from age 75, what I have is the natural log of survivors at age 85 divided by survivors at age 80 divided by the natural log of those at age 80, 75, and everything to this power. And then for A, what I have is, well, the exponential, again, natural log of 80, 75 divided by B to the 75, 5, 1. And this last expression is going to be L, the 75, times exponential to negative B, natural log of A. So now it doesn't look that scary, or at least for me, it doesn't look that scary. So let's estimate these 3 parameters and see what happens, okay? So I'm gonna get A, B, and C. Well, I think B, A, and C is better. Don't go there, Mauricio. Okay. So B is, again, I need the natural log of 85 divided by 80, and then the natural log of 80, 35, and everything goes to the power 1/5. So that's the value of B. Just be careful with the parentheses. Then A is the exponential of natural log of 80 by 75. And then this thing goes to B, not B, B, 75 times B, 5. And I think I had too many parentheses here, but I think it's working. Yes. And the last one is this times exponential to the 75 times natural log of A. This looks weird. Well, apparently it is. Okay. The best way to see if this is actually working is to estimate, to get the estimated values. So let's get the value for 75 using now this expression, right? Which is, according to this, is C times A to the power of B to the power of X. And at least for the first one, it is working because we get exactly the same value, which is what we should get. Yes, it's working. And as you can see, I can get the first three values exactly the same. I will get the same things that I had before. But now I can continue with my life table to any age that I want. Which I think this is really neat. If I want to estimate really how my population is moving, like dying at the end of their lives, that's fine. And again, it doesn't matter that I don't have this. If I want to get my individual ages for this complete life table, let me see. I have it here. So according to this is the LX. No, is this LX? So at age 99, I have 14. So at age 100. So again, what I will do here is probably re-estimate. Where am I? Okay. I could re-estimate this model, but instead of using this 5-year interval, I could use the very last three values that I have here, and then just get the same values for my A, B, and C, but instead of using N being 5, A will be 1. Yeah. But again, you don't have to do, we can combine all these perspectives. We could use one or the other, or we can just decide, okay, no, my life table is fine. I don't need to improve my life tables in any way. But the good thing about this is, okay, for the last age groups, we need information for three observed values, which again is not hard to find in your states. Okay, so again, you can, even if you don't want to use the complete life tables, something that you could do at least for the first mission is try to reach or to extend your life tables all the way to age 100. I think that would be nice, but again, you don't have to do it. But let's go back to this. What if, again, we're working with some municipality that is really small, and I only get information. I only have my information for, again, I have lots of zeros, people dying in specific ages. So I don't have that. The important thing about this method is that I only need 2 observations, right? Because what I am doing is I am fitting a straight line. So if I have 2 points, I can get the equation for that line, just getting the value of alpha and beta, or A and M, or no, sorry, it's B and M. Yes, the B is the intercept, and M is the slope. Just the same way that you did it, that you did in high school. You got 2 points, you can estimate that. So again, this is the important thing about Brass relational model, is that if I have the life table for Mexico, for my state or whatever, and if I can get at least 2 observations of well, 2 probabilities of dying, or 2 values in like somewhere in this for this small population, I can recreate a complete life table. Of course, it's not going to be as good as if I have more values, but it is something, right? And that is what we usually have to do when we don't have information for a population. Again, and I just told you, and this was 2010. This was 11 years, no, because I started in 2010 the master, so there was 2011, 2012. That was when my friend Cecilia was trying to get a life table for Bolivia. So she had some few values, and then she tried to improve it with, yes, she used brass, she used some other methods that we are not going to discuss in this semester. But that's what she did like 10 years ago. And it's not that far. That was Bolivia 10 years ago. But there are many countries that have no information, and not even from a census. Okay. So questions on this? No. I don't know why I always spend more time with the other section. I think, well, it is I am just waking up with them, so I'm really slow at the beginning. Mhm. So if there are no questions, that's essentially what I have for this morning. So tomorrow we're going to start talking about fertility. So hopefully you already downloaded your the number of births by the age of the mother, because we are going to use those things. And remember, for the activity that you have to work on these models, you only get to choose one. Well, you can either go with brass, and then you can just leave it like this, and I just smoothed my values. You can open your table and get your complete life table, or you can work with your last age groups. Again, that is up to you. Just do at least one of these things. Sorry, Cirilo. And but there's the evaluation for this part of mortality is a life table. It's a life table for something that is not life. So the idea is for you to see how life tables can be used for different things. In this scenario, is for breastfeeding, which I believe is something that we can actually study in Mexico. And I try to get information from Mexico from the last survey that we have with that information, but I was like, okay, this is too time consuming, so I'm just going to use this example from, I think it's from Nigeria. Yes, it was from Lagos in 1976. But again, it's just a life table. And at the end of the semester, as I was telling you, we are going to discuss survival models that essentially are advanced life tables. But we have the same concept. We have survivors, but we introduce some new concepts such as hazard rates and these things. Again, it's not going to be a class or it's not for you to be experts on survival models, but at least to see how these things can be applied for. I already have one example for insurance, right? So I'm gonna try to find some examples for finance, and at least 2 or 3 more examples for you to see how we can apply these concepts to other things. Okay, and Sorry, are there any questions? No? Are you still awake? No. Okay, so if there are no questions, see you tomorrow. Okay. I remember that one. Okay, there's nothing important. Okay, see you tomorrow. Have a nice day. Bye.